Hey guys, welcome to 9.2a Exponential Growth and Decay Applications. So what we're going to be doing here is we are going to be talking about growth and decay models with different real-life situations and how we can model those and make predictions. So a couple of things to note, these are very similar formulas. The growth model, we have an A value, which is the initial starting amount. And then for the decay, we also have the initial starting amount, same thing, it's the A. The R is the percent increase for the growth model, or R is the percent decrease for the decay model. So notice the only difference is the plus and the minus. With growth, as you can expect, our initial amount is going to get larger, and with decay, it's going to get smaller over time. And then T is just the time in years. So we want to write an exponential growth model or equation that would fit this. A business had a $10,000 profit in 2003. Then the profit increased by 25% per year after that. All right, so writing the general equation isn't too bad. So it's going to be y equals our A value, if we want to do this off to the side, is the initial amount of 10,000. Our R is the percent increase. And remember, with percentage in a formula, we want to convert that into a decimal. So we're going to rewrite that as 0.25. Remember, the trick is wherever your decimal place is, shift it over. Oop, started in the wrong spot. So decimal would be here, so we go 1, 2. And that's how you get the decimal version. And then the time for this case, we don't have to worry about just yet. So the general model would be 10,000 because it's every year. 1 plus 0.25 to the T. So every year it's going to increase by 0.25. So the next question asks us, what was the profit of the business after 10 years? Write your answer. We can skip over the complete sentence part, but we are just going to write this. So it's y equals 10,000. And then you can add the 1 plus 1, or 0.25. We get 1.25 to the 10th power. Now I'm going to type this in my calculator the first time around, but hopefully once you see it, I can kind of skip that step just to make this a little bit shorter. Actually, let me use the other calculator. So we would have 10,000, and then you can do parentheses 1.25 caret. Oop, before I do that, I should close my parentheses to the 10th. And then we can hit enter, and there we go. We get 93,000. We're going to round to 2 decimal places because we're talking about money. So this is going to be $93,132.26. So that is going to be their profit of the business after 10 years. And T was 10. All right, here's the next one. West Fargo's population is 35,000 people and increasing by 8% each year. What will the population be in West Fargo in 9 years? And then we're just going to skip out on the complete sentences for this one. So our A is 35,000. We are increasing, so this is the growth formula. So that is our of 8% is 0.08, and then the time is 9 years. So it's going to be y equals 35,000, 1 plus 0.08 because it's growing to the 9th. And then again, you can just type that straight into your calculator and you would get 69,965 people. Actually, I should type this in just to talk about it really quick. I don't know if this one comes out to be exact. So notice we get 69,965.16. So rather than include part of a person, we just rounded that down to 69,600 or 69,965 people. So in that instance, if it doesn't make a complete person, just round down. Okay, the amount y in grams of a sample of iodine after t days is given by the function y equals 50 times 0.92 to the t. What is the initial amount of the substance? So for this one, it's just asking you what is the A value. It's trying to get you to identify the different parts. So 50 is our A value in this, 50 grams specifically. And then it wants to know what percent of the substance decays each day. Since it's 0.92, we can tell that this is decay. And if the original amount we think of as 1 minus that percentage, so it's 1 minus the rate equals this 0.92. So you would just solve for R, and you would end up getting R equals 0.08. That's the rate of decrease, or 8%, since it wants it as a percentage. Okay, just a couple more here. Write an exponential decay model that describes this situation. Okay, notice it tells us decay, so we know it's going to be the 1 minus R. An adult takes 400 milligrams of ibuprofen. Each hour, H, the amount of ibuprofen in the person's system, decreases by 29%. How much is in the system of an adult after 3 hours? Okay, so we are starting out with 400 milligrams, so that's our A value. R in this case is 29% or 0.29. And then T, now we're not talking about time and years for this. That wouldn't make sense. So we are going in hours. So that's going to be 3 hours. So then we get 1 minus 0.29 to the third power. And this equals, if you type that in your calculator, approximately 143 milligrams. Another exponential decay model that describes this situation. The value of a new car purchased for $25,000 decreases by 10% per year. How much is the car worth after 5 years? And then we want to know after 10 years, and we can kind of talk about the differences here. So the general formula for the first one is going to be y equals still the initial amount, 25,000, and then 1 minus, since we're going down by 10%, that would be 0.1. And then it would be, the number of years is 5. So this is going to be approximately 14,762.25 if you type that into your calculator. Now the only difference over here on the other one, it's going to be the exact same equation, because we're assuming it decreases at 10% every year. We just change our exponent from 5 to 10. And this one is only at 8,716.96. So quite a bit less after the 5 years, but it's going to keep getting smaller and smaller the longer that we have it, which makes sense. And that is it